And the answer is we don't. Creative types who actually like do things for games and web pages and whatnot. I got a number that says that 25% of their time is either looking for something they've already done or recreating it. Like 25% of your time is basically just wasted. That's a scary number. Oh, I guess I should probably put the slides up on the screen so you can see them. All right, good morning. As I was saying a little bit ago, this is the last regular lecture, but it is not the last in-person session. We will have guest speakers on Thursday and next Tuesday. They will both be here in person unless something changes, like they get sick or have to travel. I know that Arpent is on the interview circuit right now. I will do a review session next Thursday to help you prepare for the final. I don't know if you've seen the Piazza thread with much more creative questions than I would have been able to come up with, which is great. I think it's absolutely awesome. And I may even use some of them. That's my task for the next week, building a final. There's not really much changed here. I did get the project 4 grades all returned, so those are available. Nothing, nothing here changed, so we don't spend much time. I actually did put several papers here. So the Byzantine generals problem is in fact a discussion that lays out the parameters of the conversation we're having today, which is about Byzantine fault tolerance. James Mickens has a very funny piece that he published in Login about Byzantine fault tolerance, and it's very cute because it's basically just sort of lampooning the whole idea of being able to tolerate these lying situations. Practical Byzantine fault tolerance is a lot of what we're going to be talking about today, so I put that paper link there as well. That was from 1999, so almost within your lifetime. And there was an interesting paper that points out an issue in practical Byzantine fault tolerance from 2021. That's not a peer-reviewed paper. It's actually just an archive paper, but it's still an interesting analysis of this. This is a real-world research area. People still do work in Byzantine fault tolerance. Any questions before I dive in? Anybody awake? I mean, it is Monday, right? Oh, Tuesday. Tuesday morning. And it's light outside. Like, that's how you can tell that the term is almost over. Just another month to go, as somebody pointed out. Any questions about previous lectures? Any funny stories? Any grand entrances? I'm going to keep today's failure short and sweet, but I thought it was very germane. It was a kernel bug, Linux kernel bug. It actually is a Byzantine fault. Not a deliberate one. It wasn't malicious. It just happened. And this is from, I love this, June 30th, 2012 at 2360 Universal Coordinated Time. Why is that weird? What happened at 60? So what am I telling you there when I said 2360? Because the next second was 24, was 0000. Yep, we put a leap second in. I'm not sure if you're familiar with leap seconds, but they are periodic minor adjustments to the clock to keep it in sync, because we don't actually have an exactly perfect 24-hour day. We don't have an exactly perfect 365.25 day year. 0.25? Yeah, some of the earliest code I wrote actually dealt with with dealing with time and counting days and doing leap years correctly. And that was when I learned, I was probably younger than you are now when I learned this, that it turns out that not every 4 years is a leap year. Originally, that's the way they did it. They created a leap year leap year was every 4 years. And over time, what happened was the clock got further and further off. And so then Pope Gregory was convinced to change the clocks, and they actually lost 11 days in the calendar. There's this massive shift from the Julian calendar to the Gregorian calendar, which is what we now use. And that was about the accumulating small error over centuries of time. So a leap second is there to try and keep things very close to being exactly where they should be. And they decide when to inject those leap seconds. Some really cool discussion about this in the Linux community about how this is really hard to get right. Because these are special cases that you can't test because they don't happen very often. This is a point we've seen over and over again in failures. Situations that really don't allow us to test them except in production, because that's exactly where you want things to go wrong. And of course, if you haven't tested it, the odds that it's going to work right when you actually run it are an epsilon band around 0. I mean, have you ever sat down and written like days or weeks worth of code and thought that it was going to run the first time? And what would you do if it actually did? It might happen once in your life if you're lucky. They added 1 second. And due to a bug in the way the Linux kernel was actually handling that 1 second, it caused some internal timers to wake every thread in the system up. Every single one got scheduled to run. What did that do? Well, that meant we suddenly had this huge spike of activity. The thundering herd, as we call it, that caused massive CPU overload. It meant that latencies went through the roof, and suddenly everything stopped working. Initially, the blame was laid on Cassandra, which is a database that people use, and ultimately was tracked down to this interesting kernel bug, which did get fixed. So hopefully that won't happen again. But these are the kinds of failures that we end up dealing with in real-world distributed systems. A bug in the way that the kernel on Linux handles leap seconds causes distributed systems failures. Oh, and Reddit went down, as did LinkedIn and the Qantas Airlines scheduling system and lots of other services. I mean, Reddit was down for like an hour and a half. It wasn't a huge outage, but it was a noticeable outage because, of course, when the internet goes down, people take notice and they say, what happened? If you're lucky, you'll never be involved in any of those kinds of the internet went down because of my code situations. But if you are involved in one of those, I guess it means you're also lucky because you're doing something that's really important because people are actually using it. We are going to talk about Byzantine fault tolerance here. And then we're going to go into the Lamport paper called Practical Byzantine Fault Tolerance, which is, for all intents and purposes, the way that most people end up implementing Byzantine fault tolerance. It's kind of like, it is view-stamped replication with Byzantine fault handling. And what was kind of cool about it is that this paper takes what could have been an absolutely hideous implementation and turns it into something that had 97% of the performance of a non-replicated, non-Byzantine fault-tolerant system, which is pretty good. But it's all in the optimizations. Maybe this will resonate with you because as you begin looking at Project 5, which is built on top of Project 4, you may have noticed that a lot of this is about, holy moly, how do we take these really slow operations and make them as efficient as possible? Why don't we run simple Paxos? It does work. We can prove it works. You can sit down and write a TLA plus proof that you have a model of distributed consensus with no leader that will work. It's not efficient, not fast. And if it's not efficient or fast, then we're not really going to be able to use it in systems because nobody's going to wait for your crappy code to converge once every millennia. Frankly, they're not going to wait a fortnight or a day or a minute. People are impatient. And then we get to go into the buzzword of the century, blockchain. Blockchain is, at its heart, Paxos. All of these algorithms, everything we've talked about, the entire term has been one bloody algorithm, and that is three-phase commit in a distributed environment using quorum consensus. And that's it. Everything on top of that is how do we make this thing actually usable? Why do we elect leaders? We don't elect leaders because it changes the protocol. We elect leaders because it makes it tractable. It makes it possible for us to use this horrible algorithm in a real-world system. And then we add things like logs, which we needed in order to build our consistent databases and provide a recovery model for what do we do when things go wrong. Because as I started this term off, and I've continued to say, this is about dealing with failure. And we get to define which failures we're going to handle and which failures we weren't going to handle. And we started off by saying, we're not going to consider Byzantine fault tolerance. We have a fail-stop model. Not a fail, continue, and spew garbage out to the rest of the world model. That's what this is. Continue, spew garbage out to the rest of the world. Oh, and by the way, we can't distinguish between you accidentally spewing garbage out and deliberately doing it. So it involves the possibility that we have malicious actors. So what we're going to do is we're going to talk about consensus with Byzantine actors, with nodes that fail and do not stop, or corrupted messages. Because remember, we started off with that assumption that all of our messages were perfectly delivered. Not necessarily that we didn't lose the message, but we either lost it or didn't lose it. Not, well, we got half the message, but not the whole message. Or we got a message that didn't say what it should have said. Because you're sitting in the middle going, hee, I'm going to change just this one bit here and send it on. And there are techniques for us to protect against that. Simple things like zero-knowledge proofs and public keying cryptography. Anybody ever looked at public key cryptography? How are your elliptic curves? I mean, we started off with prime factorization. Rivest, Shamir, and Alderman. RSA. That's factoring big prime numbers. And we know that we've gotten much better at factoring big prime numbers. Well, you don't factor big prime numbers. We know we've gotten much better at factoring big numbers to figure out if they're prime in the decades they've been working on this problem. And one of the threats of quantum computing is that quantum computers are capable of computing the prime factors of a number very quickly. So we can tell if a number is prime much faster using quantum computers. That seems to be its primary focus. There are classes of problems that are similar to that. But so we know that eventually these quantum computers will be able to split our numbers really fast. It's already become a problem even with classic processors where we now have to use very long bit lengths in prime numbers in order to make it difficult to factor things. And the numbers have gone up and up and up and now use 2,000 or 4,000 bits. And that's a general problem of cryptography because we're relying on how hard it is to compute something. Well, we can turn that to our own advantage because we're going to be able to spend massive amounts of power to compute useless information to protect ourselves against Byzantine actors. That's called blockchain. I don't know how many of you have actually ever bought or sold a cryptocurrency. Is that how you're paying your tuition bill? I actually have a friend who paid his undergrad tuition bill with mining Bitcoin in the San Jose State University's public in the computer sciences computer setup. He just used their computers. That was the old days when you could do these computations on CPUs. And then it went to GPUs. And now it's, for the last decade, it has been custom ASICs. Basically, we build our own highly optimized processors to compute SHA-256 checksums very fast. And we do it with large amounts of power. Because what's wrong with burning a few tons of coal to be able to figure out the next block in the blockchain? All right, so what is a Byzantine failure? Our friend, Leslie Lamport, lays it out in The Byzantine General's Problem, a paper that he wrote in the 1970s. That would be when I was young, younger than you are now. That's how long ago it was. And it gave us a general model of what kinds of Byzantine failure we should be thinking about and how we should think about it and how we deal with it in a distributed system. This is 1977 or 78, I think, which means that it was 20 years before he published the Paxos algorithm. Nodes continue to participate even after they have failed. This could be malicious. So they've failed because they're no longer implementing the same replicated state machine protocol that the rest of us are. So that's kind of an interesting way of thinking of failure in this context. Someone has injected a virus. They've changed the replicated state machine that you are implementing. It can also be message corruption. Now, really bogus messages are easy to detect. The ones that are hard to detect is where you make some really small change. So the basic question is, you have a city that you're trying to attack from the outside. You have, in this picture, 3 generals, but you have more than one general making the decision, and you have to decide, what are we going to do? Because we need to make the same decision. Gosh, doesn't this sound an awful lot like a consensus problem? Because it is. The interesting challenge here is that we can inject error. We can inject, in this case, it's malicious. Someone from the city has figured out how to corrupt one of the messages. So if you are General 2 and you get a bogus message, and you are General 1 and you get a bogus message, how do we actually get consensus in this situation? Is it even possible? And that was, in fact, the point of Lamport's work, which is he said, yeah, it is possible. We can come up with an algorithm for doing this. And he didn't even have to use Greek islands to explain it. So what is the goal of Byzantine fault tolerance? We want to achieve consensus. We want to guarantee safety, liveness, and that we have a valid outcome. All we need to be able to do is tolerate up to F failures. Gosh, we've seen this kind of notation before, haven't we? The network is asynchronous, just like networks have been for a very long time, and we allow Byzantine failure now. So this is no longer the model we've been studying all term. This is now a harder model, because it wasn't hard enough to get here. Now we have to make it more interesting. Let's step up and say, okay, somebody's actively trying to attack our network. Can you see why the blockchain, the cryptocurrency people like this stuff? They're dealing with money. And anytime you start dealing with money, there are people who want to take it. I mean, we live in a society where the brightest minds of the day are there to convince you to click on a link which will figure out some way of sucking money out of your pocket. I mean, everything's Byzantine at this point. So how do we protect ourselves? Messages can actually be protected using cryptographic signatures. That's why I was blathering about public key infrastructure, PKI, public key cryptography, so asymmetric encryption. We have participants that are malicious. So how do we protect ourselves against that? Oh, I know. We'll just have more people participate. Basically, the idea is you can drown out the malicious actors by having more non-malicious actors. So if you want to be able to tolerate F malicious actors, you need 3 F plus 1 participants. And then I will mention briefly at the end of the lecture the Algorand work, which actually gets this to a much more interesting result, which is they can achieve consensus with up to 2/3 malicious actors. And those academics, they went off and did a startup company. So now there's like an Algorand coin and whatnot. But it's an interesting paper. I don't know how practical this is. I mean, you can see if I have to have 3 times as many machines now in order to be able to achieve anything, wow, starts to get expensive. You're right, it is expensive. So we have to be able to handle a corrupted leader. Because if we're using a leader-based consensus algorithm, what do we do if the leader's the one that got corrupted? I mean, I could inject a political commentary there, but I mean, in a political commentary, you'd say, you mean there are uncorrupted leaders? And for liveness, we fix that by having a bounded delay, the same technique we always use. And I loved the terminology there, eventual synchrony. Eventually, in the fullness of time, we will get there within that time bound, or otherwise we'll try again, which is what we did with Paxos and two-step replication and Raft and PMMC and so on and so forth. That is the only solution to beating FLP. We put bounds. And we say, if we haven't achieved consensus within this time period, then try again. Which doesn't quite guarantee liveness, it just makes it much more likely. So, Practical Byzantine Fault Tolerance is a paper that was presented at OSDI in 1999. That would be just before one of those big clock events, which was 2000. They actually took a file system protocol, NFS, and they built a Byzantine fault tolerant version of this by using 3F plus 1. So 3F, where F is the number of malicious nodes, and they built this with NFS, and they were able to get 97% performance of a single node NFS implementation, which is why this paper got published and why this is essentially the dominant algorithm for dealing with Byzantine fault tolerance in distributed systems. I mean, you're sitting there struggling with shard masters that aren't being malevolent. And imagine if one of them was, how much harder this would get. I mean, 3F plus 1, though, is a pretty big number. That's a big price to pay for Byzantine fault tolerance. Question in the front. It's a number you pick, right? So you say, if I want to allow up to, and so like in blockchain, they allow up to 49.999% to be malicious. And they will, but they can provide guarantees. In Algorand, the whole point was that they were able to allow, I think, 2/3, something like that, 66.67%, could be malicious and still make forward progress, which is why it's kind of really cool. It's sort of like crumbling walls, where you look at it and go, wow, you can have minority consensus. Who knew? It's all in lining things up correctly. But so one of the interesting things that happens in blockchain is that it is a known weakness that if anyone controls more than 50% of the blockchain, they can rewrite history. And the mining pools are very cognizant of this. They've crossed that threshold a couple of times, and then they back off of it because they know that it becomes a real threat to the legitimacy of the system itself. And so in blockchain, it's not just that there are technical ways of solving this problem, there are also economic ways of solving this problem. It's well known, and people can see what the ownership stake is, and they can deal with that accordingly. In Ethereum, they recently switched, and I'll talk briefly about that, to proof of stake from proof of work. And the primary motivation for that was because, frankly, computing SHA-3 checksums was sucking up huge amounts of power as well, and we needed our crypto kitties, and we didn't want to pay lots and lots of coal burning to get them. So instead, what we did is we switched to a proof of stake model, but it has the same weakness. As soon as we have one consortia that agree that have more than 50% of the stake, then they can change history. And that's what we try to prevent. If they do change history, the minority will realize they've changed history and can effectively withdraw their support. But that's an economic argument, not a technical one. So the other way of dealing with those kinds of weaknesses is to make sure they're very publicly visible. And that prevents people from cheating. It's like shining the bright light on politicians. They don't like that. They're like cockroaches. Bright light, scurry. So in the practical Byzantine fault tolerant model, we have a replicated service that has 3F plus 1 nodes. It is a primary plus replicas model. View-stamp replication on steroids, because it's Liskov, right? View-stamp replication worked. It was actually understandable. So we took the understandable model of all the things we've looked at, and we just simply added Byzantine stuff to it. And by golly, Liskov delivers again. She gives us 97% of the performance that we had of no replication. And you got to look at that, and you have to say, that's actually really good, because you're giving me some pretty strong guarantees versus before when single disk drive goes and I'm dead. Not only are you giving me replication, but you're giving me replication with proof against some bad actors, some bad actors. It uses a view. Shocking. What does the view do? The view is the same thing as the ballot in multi-paxos. It indicates who the current leader is. The replicas are just replicated state machines. They are all consistent, assuming we've implemented our protocol correctly. Our state includes the state of the service, the log of the messages that are flowing through the system, and the current view. Not any different than view-stamp replication was. We add communications integrity using what are called digests and public keys. Are you familiar? Is anyone in here familiar with cryptographic hashes? I see some heads nodding. I'm not going to go into cryptographic hashes in great detail then, because I'm going to assume that you either know or you're too afraid to ask anyway, which is a win. Having said that, a cryptographic hash is a numerical algorithm that can be used to compute a value based upon an arbitrary length message with the properties that it is essentially impossible to tell what the message was from the computed value, and it is extremely sensitive to any change in the input state. So you change one bit, completely different cryptographic hash comes out. So what that means is it's very hard for you to tamper with messages. When we first started doing this, the bar wasn't very high. About several decades ago, the primary algorithm for doing this was called MD5. Today, no one uses MD5. Well, there are still systems that use MD5, but they're based on 20-year-old code. Today, no one uses MD5 because there are published attacks where we can actually change the messages and figure out how to change the messages to get a duplicate MD5 hash. So then we moved to SHA-1. About 5 years ago, a group at Google showed that for about $40,000, they could forge a message with a different SHA-1 hash value. So we moved to SHA-2. Now, SHA-1 was 128 bits. MD5 was, I don't know if it was 128, if it was smaller, probably smaller. We just keep making these values bigger, which increases the size of the space we're covering, which makes it harder for us to do this. I have to look at this because in my research, one of the things that's interesting about files is that most cloud providers compute some sort of a cryptographic hash. They all use different algorithms to do it just to make things interesting, but they do this because it means that they can say this is the cryptographic value of the file, or the hash value of the file. So when you get the file, you can say, now I can compute the hash on it and quickly determine whether or not it came through correctly. Just a checksum. But cryptographic checksums have specific properties that ordinary checksums like CRC32 doesn't necessarily have. And we're going to use them over and over again in Byzantine systems in order to ensure the integrity of our messages. One of the interesting things, like from my work, is that if I know the length of the message and the checksum, then it's much harder to forge, even MD5s. It's much harder to forge. Most of the forging methods that have been published are adding extra text to the end of an existing message. Change the message, then add the extra text, and find an MD5 that works. Public keys mean that we have an asymmetric encryption algorithm where I have a private key that encrypts the message, or it can encrypt the cryptographic hash of the message. That's a more common technique for doing it because public key cryptography is usually expensive. So we try to limit our use of it. It's computationally expensive. And then there's a public key that can be used to verify that the message was signed by me. Now, the reason we say they're public is because we need to have them available in a general way that doesn't rely on the specific channel we use to send the message. I mean, otherwise, if you don't know my secret key and you don't know my public key, you have no way of validating my message that's reliable if I just send you say, hey, here's my public key. Life's good, yada, yada. Anybody ever used SSH? SSH keys are, in fact, a public-private key scheme. They're asymmetric encryption. You generate a private key on your end, and you stick the public key on the machine to which you're going to connect. And use it with GitHub. Same thing. They don't need to know what your secret key is. They need your public key. Since they received your public key through a different channel, they now have a way of validating that the message came from you. And it's that different channel that's important here, right? We need to have a different distribution mechanism to ensure the integrity of the keys. Once we have a secure path, then we can change the keys through the known secure path. When I was doing this a very long time ago, we actually had encrypted lines. Like IBM was very strange. They required DES encryption units, hardware encryption units on the network connection over the telephone network. Now, it was a direct connection, direct telephone connection, like basically the equivalent of a piece of fiber, except it was done over a piece of copper. It was a wired line from, we were in Pittsburgh and they were in Austin, Texas, I think. So literally there was a private connection running through the telephone companies from Pittsburgh to Austin, Texas, with encryption units on both ends where the keys were manually set up. That's about as secure as you can get. Question? Manually, like over the phone or via email, or you could type it out. So how do they when you look at the way that they protect the nuclear weapons, for instance, is very interesting. They use code books that have been published. There are physically written code books, and they change them on a regular basis. And once you open that code book, it's now spoiled, right? You can't use it after that. But somebody else on some other end of the connection has the same code book. These code books have been generated, distributed physically securely. There's no electronic connection in that instance. And when you are asked to open your code book, you get to see what the code is. And if the code If the message you get doesn't match that code, it doesn't decrypt properly, it's a Byzantine message. You don't know whether it was corrupted in transit or if it was actually somebody else trying to get you to do something you shouldn't do. And those are literally, so the only way to actually build secure crypto keys is what's known as a one-use pad, where in essence, I give you a key that's as long as the input string, and I only ever use it one time. Those are secure. There are no known attacks on that other than physical attacks like compromising the actual physical key integrity. But it's not very practical. In the real world, that's not a very practical solution, but that is sometimes the solution we use for the initial setup of any kind of high secure key exchange. It's okay to pay that kind of a price when you have a lot of reliance on that. If you ever set up Kerberos servers, same thing, right? Kerberos is this system of creating temporary keys that can be used for operations. But when you actually set up the initial Kerberos servers, you want to do inter-realm keys. Those are exchanged physically in some fashion. I mean, you can put them in an email, you can send them in a fax, you could tie them to a burrow and slap it on the ass and hope it gets to there. I mean, send enough burrows with enough nodes, enough ass slapping, eventually it'll get there, but it could be intercepted. So you want something secure. So it's an exploding burrow. I've gone down. That's a really weird question. Maybe I'll put that on the final. Why do we need 3F plus 1? Well, we need a quorum amongst the nodes that aren't Byzantine. And that requires that we have 2n plus 1. Well, if f is the number of bad nodes and n is the number of, and then we need twice as many of those good nodes, and then one more for the quorum. And that's basically the essential analysis here. So it's slightly less than a third, right? That's a lot of extra nodes, but it's a hard problem. So I look at this now and I'm thinking of the Mickens article where he makes fun of this. He sends this and then he shows this like ever exploding series of graphs with more and more lines going back and forth. And it's pretty funny. But all right, so you get a request and we wait until we get more than the number of failures we tolerate plus 1 successful responses. So we could be getting responses that don't agree. Oh, that's what I forgot to put in here. I actually have this really cool example. I was going to pull it out from this game I play, World of Warcraft, because in the last expansion, there was a pair of bosses you had to fight where periodically they would go into this mode where they would impersonate 2 of the players. They were dreadlords, and the 2 players then became dreadlords because they masked themselves looking like someone else. And as a raid, as a group of people trying to fight these, some of the people could actually see who the bad actors were. And what you had to do was you had to wait until there were 2 bad actors, so you had to wait until you had 3 votes for anyone being a bad actor, because the 2 bad actors didn't know they were bad actors, and they would vote for the wrong person. So the maximum number of votes that the wrong person could get was 2, and the minimum number of votes that you needed for the right person, i.e. the dreadlord, was 3. And I think that's absolutely what we're talking about here. That's why I was like, I had a complete brain embolism yesterday, because that was, it's a great clip. It'd be like, it's like 30 seconds long, and it shows you exactly what we're talking about. We know we have bad actors. We don't know who the bad actors are. How do we determine who they are? And it's just exactly this. It's the Byzantine fault problem. Except in this instance, we decided who the bad actors were with votes. Gosh, here we're just trying to choose what the right decision is. I guess it is kind of the same thing, isn't it? So if there are 2 bad actors, I need 3F plus 1, so I need 7. I need 7 total actors, so I can get 5 good actors and 2 bad actors. At any rate. That's an interesting way. I wonder if I thought about it that way. Could I build a system where we tried to vote on who the bad actors were and use less than 3f plus 1? Ah, right. No, the issue is that you need 7 because 2 of them are bad, so now it's 5. So you need 3 votes because you need f plus 1 votes to figure out what the right decision is. So it is, in fact, exactly this algorithm. Cool. Next time, I'm going to put that video clip in because it was one of my favorite fights to do. Because I looked at it and immediately said, this is Byzantine Fault Tolerance. And it's sort of weird to be playing a video game and going, oh my gosh, this is a distributed systems problem. It's the 3-phase commit protocol. We do a pre-prepare, and then the nodes send out prepare messages, and then once we get enough prepare messages, then we send out a commit message, and then we can reply to the original requester. So this is a standard flow of a distributed system. In this case, we don't have a node that's failed. We don't actually have a node that we don't have any malicious nodes in here yet, but this is just the standard 3-phase commit protocol. This is our distributed consensus protocol that we've been talking about all semester. I had this conversation with Ivan recently where I said, because we were on the bus to go downtown for Asplos. Well, I was going home, but they were going to Asplos. We spent the entire term talking about one algorithm. The whole bloody term. And I never really thought of it that way. And then I see people describe Paxos and Raft and ViewStamp replication and PMMC as all being different algorithms. And I'm like, no, they're not. They're different implementations of the same algorithm. And it was that insight that made me understand why Lamport wrote Paxos, wrote the part-time parliament. He said, stop thinking about this as a computer science problem and think about it as a group decision problem. He wanted to remove all the idea about how do we build logs and what do we do about networks and latencies and whatnot. And he just said, hey, this is just how we decide things in a group. We spent the entire term talking about this. It's the same thing. The 3-phase commit thing is just the asynchronous version of the 2-phase commit thing. And the 2-phase commit thing came from databases where, gosh, we had a coordinator, aka leader, and we used the draconian consensus algorithm, which is everyone must agree. And we wanted something that was a little more relaxed than that. That's all we did. We took 2-phase commit, turned it into an asynchronous protocol, 3-phase commit, and then said, we don't really need entire agreement here. We just need just enough people to agree that the people who weren't around for the decision can figure out what was decided. And then all of the rest of the complexity is around recovery and making it possible for nodes that didn't agree initially to catch up. That's it. When you think about it that way, it's like, wow, cool. So mixing some Byzantine nodes in here and just ignoring them doesn't feel like it's as revolutionary now. Like, I'm sorry, but I got a quorum here. The fact that there's this minority that's not in the quorum, I don't care. I have a quorum. Within the model that I've constructed here, this is a valid approach, but it's the same approach. See, before this, we never ignored the messages. Now we ignore messages that don't agree with the consensus, but we don't know what the consensus is, so we have to actually, I may not have thought about this, but we actually have to count both sides. Because maybe the ones that we think are the right ones are actually the liars. Question in the back. Three times, right? Because that's all we need for our quorum. That's what's interesting about it, right? Is it basically, it's the exact same quorum we need if there are no bad actors. So for all intents and purposes, we've built a model where we can ignore the bad actors. The moment that we have enough votes, F plus 1 votes, the moment we have F plus 1 votes for any proposal, we know that proposal is now adopted in our Byzantine world. which is kind of weird. You're not happy with that. You feel like we should actually insist on 4? Okay. I mean, is 4 wrong? 4 is better than 3, unless it's bills. Yes. So we need a quorum amongst n minus f nodes. That's why we only need 3. And that's actually it's interesting because that's a stronger result than we get from Paxos, isn't it? So why is it we don't actually just simply need 2 in Paxos by saying that, in my cluster of 5, I'll just assume one of them is a bad guy and therefore I only need 2? That's a good question. I'm not actually sure. Right. And that's the interesting thing there. So does Byzantine fault tolerance not work if I have no bad actors? Because the argument now is in Byzantine fault tolerance, I have up to F bad actors. But if I have 0 bad actors, that is still below F. And so now I have suddenly said, oh, 7, I only really need 3. No, they don't have the correct value, but they're not necessary for us to determine a correct value. They are now behind us. We still have to do recovery on them. That's the interesting thing here, right? We still have to recover them eventually. So that doesn't change the implementation side of this, which is the reason we're allowing a quorum is because we just assume magically that there is a catch-up mechanism. And a lot of the complication in all of these labs and all these assignments and all these papers and discussions is how do you catch up? View stamp replication. The view is effectively how we caught up. Liskov and Oki laid this out very clearly in view stamp replication about how they did that. She was very elegant. I give Barbara a lot of credit for that because this was really her research. Oki was her student. And so he's doing research under her tutelage, and it's clear this is a continuation of a long line of research for her. But Oki and Liskov really laid it out very cleanly. They were very efficient in their use of messages and in the way that they recovered from failure, and they talked about how they recovered from failure because Liskov wanted to build working systems. Lamport's contribution was, he said, I don't care about building working systems. I want to understand what the model is, the algorithm for achieving distributed consensus without a leader. See, Liskov injects that leader using the view server, and Lamport's contribution really is, what if you don't have a leader? In the real world, picking network address is a technique that I saw before Liskov's paper. Well, I saw was used before Liskov's paper was published. So this wasn't like a brilliant insight. And she's not claiming that the idea of having a view server there is the brilliant insight. It was the way that they formalized it and described how they recover. Actually, recovery is the hard part here. If you did Project 4, you may have noticed that getting caught back up is hard. It's the same problem in Project 3. Getting caught back up was what made it hard. In Project 5, people keep stumbling over that. Getting caught up is the hard problem, not achieving the consensus. So here, where we talk about being able to achieve consensus with only 3 nodes out of 7, because 2 of them are Byzantine, up to 2 of them are Byzantine, it doesn't fix the recovery problem. We still have to have a recovery model. We can't ignore 3. We can only ignore 2. No, node number 3. Well, then 4 becomes a bad actor as well. Correct. If we each, given the same input, we come to different results, then one of us is malfunctioning. If we both come to the wrong result, then we are either both malfunctioning or neither malfunctioning. This was kind of my point before, is that, like, let's suppose that it really is, that it's like, how do you tell the difference between the bad actors and the not bad actors? Well, we just ask them to vote. And if we know that there can be up to 2 bad actors, the moment we get any 3 voting in favor, yeah. Good questions. Let's see. So in the pre-prepare phase, the leader multicasts their pre-prepare message. This is just 3-phase commit. I didn't spend a huge amount of time on it, but it's the same protocol. And it sends it to the replicas. I should say replicas, not backups. It changed terminology, and I try to make the terminology consistent, but I missed that one. Sorry. The leader records the message in its log, and then the replicas accept the pre-prepare message if the signature and the digest check out. So it's a signed message, and we have a cryptographic checksum on the message itself. The view is correct. The sequence number is new. I've never seen this sequence number before. And the sequence number is within the watermarks. And these are terms out of the paper. Essentially what it's saying is, these are the only regions I'm accepting sequence numbers in. So it's a window. Think of it as a window. This is the window of sequences I'm willing to accept right now, and the message has to be within that window. There are windows in Multipaxos as well. Or was it PUMC, I think, uses windows, but Multipaxos does as well. It's the same basic idea. Because Lamport uses windows for reconfigurations, which are huge changes. Don't you love the fact that we change the terms to confuse the innocent? Maybe that's the way you should think of this class. It's stripping away your innocence. If you aren't cynical about the fact that any of this stuff works at all, ever, I didn't do my job. I mean, it's kind of amazing that we can make these distributed systems work at all, isn't it? Okay, so once the pre-prepare messages go flowing out, then the individual nodes that receive the pre-prepare messages and accept them then send prepare messages, i.e. they're sending back not only responses to the proposer of the pre-prepare, but then all of the other potential participants in the network. Yes, question in the back. Okay, so this is the pre-prepare message. So in the next slide, we're just simply removing the detail of the pre-prepare message and saying, we send those pre-prepare messages to all of the other nodes. It doesn't mean that all the other nodes receive them, but in this picture, we do assume everybody receives it, because we're not really looking at the complicated cases yet. So now everybody receives that message. They each say, oh yeah, I'm good with this. And they say, I am prepared. Think about this in the Paxos terminology, which is we propose something and these are now accepts on the proposal. It doesn't mean that the proposal is accepted. It just means that I'm willing to accept it. And now, everyone who receives enough of those prepare messages says, I have now seen that we have achieved consensus. In this regard, it's a little bit different than the way that PMMC and Paxos implement, because in the strict leader environment, it's the leader who gets to collect those votes and then make that decision. Here, we actually are not as rigidly tied into that leader, are we? It's like we're just telling everybody, because we don't know who to trust at this point either. Because remember, if we trusted the leader, we wouldn't be down this Byzantine Fault Tolerant line. So this is a slight variation, actually. I would argue this is not quite the same protocol. Conceptually it is, but the details, the implementation details now require that we send this to everybody who's participating, not just the leader. So we've weakened the role of the leader here. Still the same algorithm. Because even in the original Paxos and multi-Paxos, you were allowed to broadcast things, especially in Paxos. So now every node that receives enough prepare messages from other nodes to count the quorum, once it says, I have enough, now it sends commit messages. All of the nodes that receive that commit message then can send replies back to the original client. Question in the back. There isn't anything. That's why all of the actors have to send the message back to the client. In this instance, the client needs to get enough commit messages back to know that the command is committed. Because remember, he has to tell us which command he committed and what the result was. So if you get those results back, and there are Byzantine actors in here, they're going to give you the wrong result. But you can ignore them as soon as you get 3. Well, I'm not even going to say that because that was specific to that example before. You can ignore them once you get enough consistent commit messages to know that you have the majority decision. But you could get messages that say, yeah, we decided something different. Question. The clients have to know in this case, yes. So that is a difference than the model that we've used before. Now, of course, we can build the model we did before by just simply adding, making this client in this instance part of our system, and then making the client that talks to this client external, right? Yeah. And realistically, the way you really implement this is you put it into a library that somebody building an application calls. So it doesn't have to be a distinct client per se. And now you have Byzantine fault tolerance. It does complicate the client a little bit. Not that bad, though. There are lots of details in this paper. It talks about garbage collection. We know how hard garbage collection can get. We've seen failures in both the projects and in the failure discussions. Oh, gee, I was a little too aggressive at taking the garbage out. I mean, have you ever thrown the garbage out and then realized there was something in there you shouldn't have thrown away? Yeah, well, welcome to distributed systems. The alternative is you become a hoarder, in which case you never throw anything away, and that's another potential problem. You can easily clog your storage up with logs. Question in the back. Yes. Yes, the reply is the committed message. It didn't label on this on the diagram that I stole, it didn't label it as committed, but in fact in the paper it actually says this is the committed message. So I get enough commits from other people and now I say, okay, I've committed this. This is what I committed. And so the message that you send as the committed has enough information in it to be able to confirm that what was the outcome. And the client then will get a bunch of these messages, sift through them and say, okay, I got a bucket of F that I don't trust, and I've got a bucket of F plus 1 that I do trust, and now I'm done. Yeah. It's a very chatty protocol. Yeah, it's a broadcasty protocol. You say committed. Yeah. Yeah. Yeah, it's interesting because it's not quite the same as the protocols we've seen before, but that's because we now have this motivation of shifty characters. Just look around the room. Do you trust the people sitting next to you, behind you, especially that one in the back corner? View changes are complicated, but they do happen, and it's discussed in the paper. And now you can sit there and say, thank God this isn't Project 6. It could be a really fun project, though. Maybe I'll do that next term if I teach it. I'll say, we're just going to implement Byzantine fault tolerance. We're going to build our own blockchain. And that leads me to blockchain. I was like, ooh, I need a good blockchain slide. So I went to my Adobe stock account, which I have, like a couple hundred free, which means I've been paying for them pictures that I can use. And so I grabbed one. It was like, this is cool. This has got so much detail in it. People will just look at it and they won't see anything. Perfect. No questions. This is actually not that different than practical Byzantine fault tolerance in a number of ways. It's not the same, though. We really don't trust people. There are elements of this that relate to why we actually can build a system. Like I said, there's a weakness in it, right? The weakness is that once somebody controls more than a majority of the individual nodes, then we can no longer guarantee that history becomes immutable. And that's a weakness in it. But we published that weakness. And then again, in Byzantine fault tolerance, we weren't allowing us to have, n plus 1 over 2 faulting nodes. We had f, and f was quite a bit smaller than the total number of nodes. So, okay. We don't trust anybody in this model. But we give them incentives to behave, and that creates a non-technical argument for why people won't actually try to play us too much. Now, having said this, there is a tremendous amount of work that has been done in analyzing blockchains and looking at how you can actually cheat. And if I had time, I'd go through them, but I don't have time, so we'll skip it. The problem of electronic cash is one that people have been working on for quite a while. There was a fair bit of work done in the early 2000s, and the big problem that emerged from this is what's called the double spend problem. How do I know, as the recipient of an electronic coin, how do I know that you haven't spent the same electronic coin with somebody else at the same point in time? Gosh, this is a distributed problem, because we want a single outcome. You give me that coin. I don't want someone else coming along, hey, I got that coin too. And this was a real problem that they dealt with. And of course, it is a distributed systems problem, so it ended up creeping into the distributed systems community. But the actual party used a pseudonym and published this paper in 2008. Published this paper. They put it on the internet at a website called bitcoin.com or .org. Bitcoin.org. And I don't believe, there's some guy down in, I think, New Zealand or Australia or something that claims to be Satoshi Nakamoto, but it's not entirely clear that they are. The best evidence we have is that the initial block of coins actually contained like 6 million Bitcoins that belonged to Satoshi Nakamoto. And they had never moved. They moved like last year. Some of them moved. And so that means that somebody has a private key. It uses a private public key system. It tries to solve the double spend problem. And in fact, the paper explains why you can't double spend in this anymore. The basic unit in this is the block. The block of transactions. This is a balanced set of operations where the inflows and the outflows match. I've got a very nice picture from Accounting 101, which I'm going to use to explain the basic concept here. The block itself is public and it is easily verifiable. It turns out that computing a SHA-256 value on a known block of data is a fast operation. We're going to make it hard because that's the mining part. Interestingly enough, what it's actually implementing is a distributed timestamp service. So what they did was, remember what Google did to get the same timestamps? They put atomic clocks in and they had windows. Well, this is a distributed timestamp server. So we can agree on when transactions happened. The concept of a blockchain, and I just stole these pictures directly from the Nakamoto paper because they're simple enough, they make the point They get across cleanly. So the idea that the reason it becomes a chain is because you use the hash value of the previous block in computing the hash value of the current block. Thus, if I want to change something in this block on the left, I would have to recompute the hash value for the block on the right. So all of the future operations are tied or linked into a chain of things that have already happened. This means it's difficult to rewrite history. Not impossible, but difficult. It becomes computationally infeasible after about an hour on the blockchain network. And there's a lot of computational power on the blockchain network. They burn several coal plants worth of power every minute, computing SHA-256 values. See? Accounting 101. How many of you have taken an accounting course? Oh, wow. Quite a few people. So you're familiar with double entry bookkeeping. So the idea is that in a ledger, I have offsetting entries. No matter what is on that ledger page, the numbers in each of the columns add up. So in the blockchain, inputs and outputs balance. So if you put a coin in, because let's say you're going to buy your cup of coffee at Waves with your Bitcoin, you give them your Bitcoin, that pays for your coffee, but you get change back. So we take that coin in, and then we generate a coin out, and that's your change. We generate another coin out, that's the money to pay for your coffee, and we generate another coin out, and that is the cost of the transaction. And those two things balance. Each of those is a transaction in this block of transactions. Those blocks in Bitcoin are actually 2 megabytes in size. So you can only fit a finite number of these transactions within that. That entire block is then hashed. We take the hash value of the previous function of the previous block, and we include it in the hash value of the current block. And we leave one field, one little field there in the block that's called the nonce. And that's the part that requires we do the work. This is known as proof of work. A nonce is literally a value that does not matter. The only reason we have the nonce is so that we have to do some work in order to prove that we've validated this block of transactions. Why do we create that? It's the disincentive for malicious actors. They have to spend real money because they spend energy to compute a value of a nonce that satisfies a requirement. And the requirement in Bitcoin is how many bits are zero. The leading bits. How many of the bits are zero? And that number is adjusted so that approximately every 10 minutes a block of transactions is approved. It's statistical, so we don't guarantee exactly 10 minutes. What is the incentive for someone to compute that nonce? Well, one of the transactions on that page is the one that creates new Bitcoins to compensate them for their services. The number of Bitcoins that are generated is on a decaying balance. Approximately every 2 years, it falls to 50% of the previous value. I think it's like 12.5 or 6.25 now. I don't know what the last change was. So 6 Bitcoins is, I don't even know what the price of Bitcoin is anymore. Probably about 120,000 US dollars. Assuming 20,000. Does anybody know what the cost of Bitcoin is right now? 37,000 US or Canadian? So 37,000 Canadian is about $4 US. So, hey, I get to convert money the other direction. It's nice to get like this 30% bounce every time I take US dollars and turn them into Canadian dollars. So that would be probably about 30,000 US, roughly. Close enough. So $30,000, you get 6.25 Bitcoins. That's almost 200,000 US dollars, 190,000 US dollars. 37,000 times 6, whatever that is. About 230,000 Canadian dollars. Can you see why that's an incentive for somebody to spend some energy to compute these blocks? Yeah. $40,000. Crazy. The only way you can actually find that nonce is by trying them. You remember when we were talking about sharding problems and then accumulating the results? This is a very classic parallel, embarrassingly parallel problem. The way that we do this is we have lots of different people computing different pieces of the nonce space until we find a block of transactions with a nonce that, and we pick the transactions based on which ones will make us the most money, because remember, we get paid for each of those individual transactions. And we just divide the key space up, and once we actually compute that, then we present our proposal. So what we're doing is, in essence, limiting when we send proposals. People can look at the proposal and say, this isn't a valid proposal. That's something that's not a concept in Paxos. This is the Byzantine aspect of it. So that proposal now comes in across the network because it floods the network, and you sit there and you look at it and you go, oh, I know how to compute SHA-256 values really fast. Here's the hash of the previous block because it's been accepted. Here's the hash of the previous block. I put that in, I compute the hash on that, and I verify, yes, with this nonce, I do get the same hash value you just reported. So I'm willing to accept this because this is a valid proposal. And that's our digest in this case, is that nonce plus the hash value across the transaction block. So it's very easy to confirm one of these blocks. And once enough people have confirmed that, then they say, okay, now it's time to work on the next block. Because that block's now been accepted. And now I start working on the next block. Blockchain actually does have a mechanism for doing garbage collection. What they do is they don't actually store it in a flat ledger. They store it in these things called Merkle trees. And Merkle trees are a common way of dividing up spaces that use large cryptographic hashes, as it turns out. And it allows you to prune pieces of the Merkle tree that have transactions you no longer need to maintain. So this is just a very interesting garbage collection technique, because effectively the ledger is a huge log. We have a globally replicated log of, I haven't even looked, it's probably 100 gigabytes now, 150 gigabytes. I mean, at one point I used to run a node that just kept the log. So I could do very fast transaction searches. You can walk the transaction chain, you can see what happened. When you prune things out with the Merkle trees, though, you eliminate your ability to see transactions that happened inside of things where there's no state that we need anymore. So there are people who save. They don't garbage collect. They can actually save everything. So the advantages of blockchain versus practical Byzantine fault tolerance is that we really do have totally decentralized consensus. We don't really have a leader here. We barely had a leader in pBFT. Remember, where we were like, everybody was talking to everybody else. So it was not that different. It does work against Byzantine failures, and it works on unreliable networks. The problem with pBFT is that it requires an awful lot of faults. So introducing this proof of work concept actually solved some of the big overload in practical Byzantine fault tolerance. There's a lot of communication costs in pBFT. A lot of that paper is about how do we minimize this extra messaging. And when you use broadcasts, that helps eliminate the amount of network traffic. If you actually have to simulate broadcasts with lots of directed unicasts, then you can see that the message traffic gets very high very quickly. I'm not sure that's entirely a plus, because in actual Bitcoin networks, there's a huge amount of duplicate messages that get sent. Huge. Because they don't use broadcast, they mostly use replicated unicast. Now, the Byzantine consensus for timestamp chained ledgers is not explicit in the Nakamoto paper. That's something that has been introduced as we've generalized blockchain from the original Bitcoin work. It is limited in terms of participation because miners are people who are willing to spend the energy to do the actual mining. Bitcoin was interesting in that it incented miners But it's a diminishing returns thing too, because the next time they cut it in half, it'll only be 3 1/8. And then after that, it'll be 1 1/16, 1 in 5/6. And you have to have good cryptographic hardware. For all intents and purposes, all Bitcoin miners for a decade have been custom-built ASICs with really big power supplies. You haven't been able to mine, even with GPUs, in at least a decade. Ethereum and a number of other cryptocurrencies, Ethereum did use a different cryptographic checksum. It used SHA-3. And SHA-3 doesn't, part of its design was to be very different than SHA-2. It's not stronger. It's intended to have a completely different approach to solving the cryptographic hash problem, so that if SHA-2 were compromised, we'd have something else that we could use. It uses what are called sponge functions. And sponge functions have a very different actuation than SHA-2, where SHA-2 are much more traditional shift and substitute style. SHA-3 was also designed to not be easy to implement in hardware, interestingly enough. Ethereum has recently switched away. Let's see. So other readings here, since we are now at the end and I'm going to finish this up. Algorand, which was presented at SOSP 2017 in Shanghai. I was actually there. It was before the world changed, when we didn't have weird things going on. Algorand has turned into the DeFi company. And if you hear someone saying DeFi, they're probably trying to scam you. Just a heads up on that. Ethereum has recently switched to proof of stake. That was done last year. It took them years and years and years to make that switch. So it has much lower energy consumption, but the consensus is now based on ownership. Do you feel weighted quorum? Because that's basically what they've done. They replaced their quorum consensus algorithm with a weighted quorum model. Okay. And this is where we find non-fungible tokens. And just as a heads up, if someone starts telling you how they have great opportunities in NFTs, they're probably trying to scam you. But this is how we got CryptoKitties, which were invented here in Vancouver. Interesting uses. See, I have this interesting observation. I get lots of people who talk to me about blockchain, and it's used very heavily for scams, but there are some legitimate uses for it. And one of them is as a land title registry. And so there is a paper on using a blockchain approach for land title registration in Bangladesh. In countries where it's not uncommon for land title records to suddenly change the ownership, that's rewriting history kinds of things. This is a really useful use of a blockchain. It provides you with a distributed consensus on who owns what that's impossible, almost, to tamper with. And that's really an interesting problem for which we have no other good solution. So there you go. Byzantine fault tolerance. We talked about Byzantine systems, practical Byzantine fault tolerance, and blockchains. And now you can see that distributed systems is still a researchy topic. These are literally things that have happened recently, and we continue to do work. We had a master's student a couple of years ago who did some small work, but it was some important work in improving performance in actual blockchain. And his work as a master's student was published and adopted into the way that Bitcoin works. So this is real stuff. This isn't imaginary, make-believe stuff that happened before you were born kind of crap. This is happening today. Any questions? You're almost done with having to listen to me this term. Almost. Maybe I'll record a couple of things and tell you they're mandatory for the final. That's too much work. I'm lazy. I don't want to do any proof of work stuff. Great. That's it. We have a guest speaker on Thursday. It will be here. As far as I know, if anything changes, I will definitely post it on Piazza and probably mumble something on Discord. Office hours are today at 1, if anybody shows up. I don't think anybody showed up last week. No, people did show up for Zoom office hours. No one showed up for Discord office hours last week. That was it. I sat there for an hour and picked flowers and